Okay, so first let me thank Arnab and Pinaki and Arnab students for the hospitality in the last week. I'm Yuval from the School of Chemistry in Tel Aviv, and today I'll be talking about gating, which is my main PhD endeavor in the last few years, gated reactions, or in more generality, gated first passage processes. And my main objective here today is to introduce you to this concept, which is maybe not really known in this community, and give you a tool to explore these processes, to explore gated problems very easily, actually. So I will begin with a motivation from the perspective of a chemist, which is a simple reaction. The most basic model that we can think of would be the Smoluchowski type reaction, diffusion-controlled reaction, where we put one of the particles in the origin of our coordinate system, and we let the other react and diffuse relative to it, and we say that reaction occurs on contact. And in more modern terminology, if we look at the mean reaction time, this is the quantity that we are interested in, so simply the mean reaction time will be the mean first passage of that particle to the origin. But as I said, this is a relatively simplistic model, and the next step, a few decades later, was introduced by Collins and Kimball, where they have considered partial reactivity. So now every time that the two particles collide, there's a certain probability of reaction and a certain probability to not react, and we will denote the probability to be reactive on collision by R. So let us calculate the mean reaction time for this model. It's actually a very simple calculation. The first term remains. The particle, of course, still need to meet for the first time. But now what would be the additional contribution? So after they meet, we ask the question, did the particle react or not? If they did not react, they need to meet again. Now this is not a first passage process, it's a first return process. And after this first return, after they return, we ask the question again, did they react or not? And we do it again and again. Essentially, this is just a sequence of trials, geometrically distributed, with this probability by R to react, and we know the number of attempts is just 1 over this probability. That will be the mean of this distribution. Each trial will take on average the mean time that it takes it to return, and the contribution will just be that. So I'm claiming that this is still relatively simplistic, at least at certain cases, because here we neglect correlation, and by that I mean by assuming that every time that the two particles collide, we are neglecting correlation between the internal dynamics of the particle, of the system, if such internal dynamics exist, and the spatial process and the return process. And that is essentially where the theory of gating is needed. And maybe to illustrate that point even further, here is a cartoon. So let's say that the particles collided and did not react. So we know that the system is in the non-reactive state, where the two particles are at distance 0. Now consider two different trajectories possible. One of them is very short, and one of them is a very long trajectory. So if I was non-reactive to begin with, you might expect that after a very short trajectory, I have higher probability to still be non-reactive versus a very long trajectory where the internal dynamics have enough time to equilibrate. And that is exactly the correlations that we talked about. And why we call it gating, because in biology and in chemistry we imagine an entity such as a ligand or an enzyme that has a part that acts like a gate that opens and closes, and only in the open conformation it can admit the ligand. But for the remainder of this talk, let us make it more abstract. We have just two states, a Markov chain, a reactive state and a non-reactive state. And it actually doesn't have to be a chemical reaction. It can be any first passage process and any set of constraints we call the set of constraints. If they are fulfilled, we are in the reactive state. If they are not fulfilled, we are in the non-reactive state. And just an historical comment, the theory of gated reactions in the macroscopic case at least is studied from the 80s by McCammon, Shop, Szabo, many other people, and it's actually is getting renewed attention in the last years, where people mainly deal now with the microscopic single particle problem. But there are a lot of works, and when me and Shlomi Reuveni from Tel Aviv consider the problem, we didn't want to just solve a specific case. We want to build a tool to study this kind of reactions. And we started with CTRW, continuous time random walks. So we are in continuous time discrete space. And these are the rules of the game essentially that we are postulating. You can have any network, means any dimension, any connectivity, and any spatial dynamics on that network. It means that the waiting time in each site doesn't have to be exponential. And also, of course, it can be non-homogeneous. Every site can have different waiting time. The only thing that matters here is that once we set the rules, they do not change with time. So on every iteration, if the particles did not react and they need to meet again, the network is not changing in time. So that is a complete generality except that. And we now divide and rule. We start by looking at the internal dynamic system, which is simple. And we define the relaxation time of the system and the equilibrium occupancies pi r and pi r for being reactive and pi not reactive. And the only quantities that are of interest of us, they are sort of the internal dynamics propagators, or just the conditional probabilities. If you started in the beginning in the non-reactive state, after time t, what is the probability that you will be reactive or non-reactive? All of these four combinations. So once we have this, we are good to go. And we now tailor it with the spatial process. So how do we do it? So let's say the particle started at a certain location, R0, in a certain state Q0. The first leg is actually simply a first passage. So we all know it from like elementary books. It's just the regular first passage. But now what happens? The way we deal with it, we write an indicator function. If the particles if the system is in the reactive state, the game is over, so this indicator function will get the value 0, and if not, it will get the value 1, and we continue from here. So now we are at 0, it means on the target, and in the non-reactive state. So while this is a classical quantity that we know how to compute, this random variable is actually a little bit more tricky. And the way we compute it is we identify again that this is actually a renewal moment. So I will write the renewal equation, but since it's a short talk, I don't think I have enough time to talk about it in detail. But essentially, we are asking, okay, once we arrive, did we switch on the target or not? If we did not switch on the target, we wait a certain time, then we come to this point, and we have to come back again, and again we ask the question, did we react or not? Is an indicator function, and this random variable here is IID, is independent and identically distributed as that one. So taking the mean of this renewal equation and the Laplace transform, we can get all the quantities that we want. So I will just show you the results, and we will not do it together. For the mean, so if I started at 0 in the non-reactive state, how much time it will take me to react in this gated reaction? And that is the equation. I want you to notice two things. One is that on the left side we have the gated quantity, the mean reaction time. But on the right side we only have the parameters of the problem and the first passage quantity. So on the right hand side we only have the ungated problems quantities, and that means that if I know to solve a simple first passage problem, I simply plug it in here, and I have already the result for the gated reaction. Another thing I want you to notice is that the notation might be tricky, but that is the mean of the first passage time, and that is the Laplace transform evaluated at the relaxation rate. So essentially the entire distribution of the first passage time is getting into play. It's not just the mean that affects, it's the entire distribution, and that means that fluctuations in the return time, they are all getting inside the mean of the reaction time. And so we'll do two checkups. One is we will take the limit of very fast relaxations, and if we will do it, if the system transitions very, very fast, we actually return back to the scenario of like geometrically distributed partial reactivity, what we have seen earlier on. This is simply the average time that you wait on the origin before you leave, and that is the time that it takes you to come back. So it's essentially the first return quantity, the mean first return time. Another thing that I will show you is what happens if you vary the fluctuations now in the return time, because we have seen that it's dependent on the entire distribution. So let us take a few distributions, all of them with the same mean, and just the only difference would be different fluctuations in the return time. And you can see how, so we quantify, maybe it's not known, the fluctuations by what is known the coefficient of variation, which is simply the ratio between the standard deviation and the mean. And as this quantity increases, you can see that the mean reaction time is getting larger, and actually the black curve here is simply deterministic case, so it's deterministic return time. Okay, but not always we have a finite mean, so in these cases we can also take the Laplace transform of the PDF and get a similar, a little bit more complicated, but essentially a similar relation, where you see that on the right hand side you only have quantities like the Laplace transform of the first passage, the regular first passage, the ungated first passage problem, and on the the left hand side you have the gated PDF. And we can, so it means that if you know how to solve a first passage, you can just plug it here, and again you get the gated result very easily. And that is just a demonstration how to do it if you are considering CTRW on the 1D line. So we know how to get the first passage PDF, and simply by plugging it in the formula above, you get the solution, and it agrees perfectly with simulations. And also we can explore the general formula that we have and see general effects that happen to gated reactions. So we have general formulas. For example, we can see here that the asymptotics is inherited. Just the power law is changing, and we can determine exactly what would be the prefactor. Another interesting thing that we can see is that if you spend a lot of time in the non-reactive state, it's called the cryptic regime. So most of the time you're spending hidden. It's hard for you to find the target, or it's hard for you to react. You have a very, very long, over a few decades here, interim regime that has a completely different power law. So initially you can think even that you have different asymptotics, and we can exactly determine what would be this power law and what is the prefactor. And this kind of general calculation we are doing in this work and in other works. And finally, numerics. We have also shown that sometimes instead of it might be a difficult problem if you don't know how to solve the problem analytically, you have a very large parameter space if you have to probe the entire alpha, beta lines. So what you can do is just simulate the regular first passage process and plug it in the formula, and then you get complete agreement as if you have simulated the entire phase space. Yeah, these are the main things that I wanted to show. We have other works we have explored after that, discrete space and discrete time. A very new work that is now on arXiv is the continuous space and time analog, where we also consider entire volume like an interval that is now gated, that might have a lot of applications in biology and so on. And another application, another direction that we have recently uploaded to arXiv is the reverse problem, where we want to infer. All we know is the detection time, and we are trying to find the first passage time or the rates in which the system transition. So we also give a lot of motivation, where in reality, in experiment, there are cases where you can only measure the detection time. And these recent applications, you can also find them in a poster by engineer Kumar from Pune, our collaborator, and if you want, go talk to him and he will explain even more. I have more time, I guess. But, okay. Yeah.
Can you apply this to actual chemical reaction networks, where the state space consists of sort of all the combinations of copy numbers?
Oh, the combination of copy numbers, that I'm not sure I understand. When you have multiple states.
So if you have a chemical reaction network, the state is specified by knowing all the copy numbers of each of the types of molecule present. And then a reaction, in principle, is also a walk on that network somehow. So would what you're doing work in that context?
That is a single particle.
You have a single particle that's representing the kind of state of the multi-particle system.
Yeah, we'll have to talk about it. Once you add averaging over multiple targets, the problem it's a little bit more complicated. It depends now where is the gate on, which particle is doing the gating, and
okay.
But you can actually, so we have solved it for a two-state system, maybe some sort of a coarse-grained picture, but you can definitely solve it for a multiple-level system. Mm-hmm. The copy number, we should discuss it.
Okay, well, we can talk offline.
Yeah, sort of a related question. There have been a lot of experiments on single enzyme kinetics, who? Sunny, correct, by Sunny Z. And they look at the modification of the Michaelis-Menten kinetics coming from, single stochasticity of particle encounters and state changes and so on. Have you, it will be okay to compare that might be a good experimental system to look at and compare your results with.
So the last project is actually a build-up for that. We are really, we wish to find the experimental system to finally show that it can be measured. Usually it's a problem to do it in the forward direction, but we hope that maybe in the inference problem we'll get some luck with experiments. The Michaelis-Menten is a different scheme and perhaps can be related to that. We have thought in this direction, but it has some more components, and this is like a little bit different than that. So I should also inquire about those experiments of Michaelis-Menten. But you're saying these are single particle.
Yeah. There were very nice experiments on this. And the other extension is to look at multi-state Markov process, which might be, let's say, 3-state Markov process rather than a 2, but which violates detailed balance. And then there are lots of chemical reaction dynamics which are driven out of equilibrium. So
We have other motivations also to go beyond the two states. This is just the simplest possibility. We wanted to cover that, but at least 3 states, there are many stuff that leads us to go in this direction as well.
Okay. Thanks. If there is no more questions, I will thank Yuval for this nice talk.